Hello AP Chemistry students. These are your notes for topic 8.3, acid and base equilibrium. So the enduring understanding is that the chemistry of acids and bases involves reversible proton transfer reactions with equilibrium concentrations being related to the strength of the acids and bases involved. Our goal for this lesson will be to explain the relationship between pH, pOH, and concentrations of all species in a solution of monoprotic, weak acid, or weak base. So first, let's recall that an acid is a substance that donates a proton, and a base is a substance that donates or that accepts a proton. So in this example, we have an acid, and water acts as the base, and so our acid donates its proton to the water, forming hydronium, and we end up with our negative ion as the conjugate base. In this example, we start out with a base, and it's going to accept a proton from water, which acts as an acid, and so we'll end up with ammonium and hydroxide. There are 6 strong acids: hydrochloric, hydrobromic, hydroiodic, all halogens, and then perchloric, sulfuric, and nitric acid. All other acids are considered weak acids. So our strong acids, when they participate in reactions, will go to completion. But our weak acids, when dissolved in water, only a small amount of ionization actually occurs. And so we get the general equation where HA denotes any acid. So we'll have HA plus water will produce hydronium ions and the negative ion from our acid. So since this is an equilibrium reaction, we're going to have an equilibrium constant. We call it Ka when the reaction is for a weak acid, and this is called the acid ionization constant. These constants are generally very small, and sometimes pKa is reported instead of Ka. So Ka being very small means that this reaction will tend to favor the reactants. So we end up mostly with the unionized molecular form floating around in our solution. And so you can see that over here. We mostly have our HA particles floating around in the solution with the occasional acid and hydronia, or negative ion and hydronium floating around as well. So a weak acid, for a weak acid, the smaller the Ka, the larger the pKa, and the weaker the acid. Okay, and then Ka is represented by the concentration of the hydrogen ions times the concentration of the negative ions divided by the concentration of the molecular form. Our strong bases include group 1 and group 2 hydroxides, and recall that our strong bases are going to completely ionize. All other bases can be considered weak bases. And so when a weak base is dissolved in water, a small amount of the base will react with the water to produce hydroxide according to the following general equation. So B represents any base, and when added to water, the water is going to act like an acid and donate a proton. So we get Hb plus and hydroxide. So since weak bases also react with an equilibrium reaction, we'll end up with a K value, Kb in this case for bases, and that's called the base ionization constant. Since these constants are generally very small, pKb is reported instead of Kb. And the smaller the Kb, the larger the pKb, and the weaker the base. The weaker the base, the smaller the Kb, the more the reaction favors the reactants. And so we end up mostly with the unionized form of our weak base in the solution. So we can see in our particle diagram that our weak base is found frequently in our solution, the unionized form, and then every here and there we have a hydroxide ion and our Hb plus. So Kb is equal to the concentration of the BH plus the times the concentration of the hydroxide ion divided by the initial concentration of the base. So percent ionization then is a measure of the extent of ionization of an acid. A strong acid will have 100% ionization. The same is true for a strong base. So we can calculate percent ionization by dividing the equilibrium concentration of the hydronium ions divided by the initial concentration of the molecular acid and multiplying by 100% to convert to percent. This can be calculated for either the acid or a base. So percent ionization is dependent on both the strength of the acid or base and the initial concentration. If acids are of equal concentration, the weaker acid will have a lower percent ionization because it is more likely to be found in that molecular form, the unionized form. If two samples of the same acid have different concentrations, the solution having the lower concentration will have a higher percent ionization. So here's our quick check problem. A pH of 0.036 molar nitrous acid HNO2 is measured as 2.4. The percent ionization for nitrous acid is what we want to find. So I'm going to start out by calculating the concentration of my hydrogen ion using the given pH. So to do that, the concentration of H plus is equal to 10 to the minus of the pH. And so that's equal to 10 to the minus 2.4. And then this comes out to 0.00398. And I'm going to keep a couple of extra digits right now. I know that doesn't match my sig figs, but I don't want to introduce any rounding error in my calculation. So percent ionization is equal to the concentration of the hydrogen ion at equilibrium divided by the concentration of the molecular acid initially times 100. And so I'll have 0.00398 divided by the initial concentration of my acid, 0.036, and then times 100 to convert to percent. And this comes out to around 11. But remember that in my pH, the significant digits are all of the places after the decimal. And so I only have one significant digit here. So that means I have to round this to 10. And don't forget to label your percent. So on your equation sheet, you have three equations that are related to acids, the Ka, the pH, and the pKa. We have three equations related to bases, the Kb, the POH, and the pKb. And then we have two general equations. So Kw is equal to the hydrogen concentration times the hydroxide concentration, which at room temperature is equal to 1 times 10 to the negative 14. Kw is also equal to Ka times Kb. And then based on room temperature again, 14 is equal to pH plus POH. It's worth noting that the significant digits here, 14 is exactly 14. And so if you have to do any calculations with that, the 14 does not turn the significant digits. So here's our I do problem. So the pKa of hypochlorous acid, HClO, is 7.54. What is the pH of a molar solution of HClO? Well, let's start by determining our Ka. So Ka is equal to 10 to the negative of our pKa. So that's equal to 10 to the minus 7.54, which is 2.9 times 10 to the 8. I'm sorry, 10 to the minus 8. Okay? And so next step, I need to do an ice analysis. So I'll have HClO produces H plus and ClO minus both aqueous, and I'm simplifying here. I left out the part about the water, but it doesn't matter for our ice calculations anyways, because we'll leave it out. So my initial concentration of HClO is 0.100. Okay, my initial concentration of the hydrogen ions is 0, and the hypochlorite also 0. So since I have a 1:1:1 mole ratio, I will have just 1x for each of these. And so I'll have at equilibrium 0.1 minus x, x, and x. So now I need my expression for Ka. So Ka is equal to the concentration of the hydrogen ion times the concentration of the hypochlorite divided by the concentration of the hypochlorous acid. So Ka is equal to x times x, so we'll put x squared, divided by 0.1 minus x. And all of this is equal to the Ka value that we calculated above, so 2.9 times 10 to the minus 8. And since 10 to the minus 8, this Ka value is very small, less than 10 to the negative 4, I can actually ignore this minus x when I solve. And so I'll get x is equal to 5.4 times 10 to the negative 5th. But again, this is equal to the concentration of my hydrogen ion. And so the last step then is to calculate the pH. So the pH is equal to the negative log of the concentration of the hydrogen ion. And so this is equal to the negative log of 5.4 times 10 to the minus 5th power. And that comes out to 4.27. Remembering that I have two single digits here, so I'll have 2 places past the decimal in my pH. And now for the redo. We want to calculate the percent ionization for a 0.155 molar solution of acetic acid. The Ka is given at 1.6 or 1.76 times 10 to the negative 5th. So I'm going to start out with my ice table. So I have acetic acid